Welcome to the deep dive on the graphing quadratics unit. So, you have undergone a massive journey and you've learned so much by this point. Congratulations for getting here. Most of the SAT that determines if you get into college is about this quadratic stuff. And let me show you why. First of all, there are tons of competencies that we as teachers have to prove you have scored well enough on in order to be considered good enough at this competency to graduate. And so these units have a lot of these competencies in them. For example, one of the competencies is solving for x, which specifically happens with linear equations in year one, and then exponentials as well in year one. So linears, if you graph a linear, it makes a straight line. So linears look something like this, and it's a straight line. Whoop. And then exponentials have x in the exponent, like up here, the exponent's an x, and that makes it kind of curvy. So in year one, you have tests around these two and proving that you can solve for x. Quadratics is a huge part of year two. A lot of year two is around solving for x with quadratics, and it's so important it comes up again in year three as well. Cubics and other higher degree polynomials will come up in year three. Trig functions are in year two. It'll be one of the next couple units, and then circles are also in year three. And so those are where you'll prove this competency. Then there's the competency where you have to go between the situation and the table and the graphs and the equations. Again, linear and exponentials are in year one. Quadratics are in year two, as well as cubics and other higher degree polynomials and trig functions. We'll do all these this year, and we just finished quadratics. And then there'll be circles in year three. Also, being able to determine key features of any of the types of functions, and then being able to analyze them like in terms of the situation. You do linear and exponentials in year one, quadratics in year two, and then the rest of them for this one in year three. So you'll also do quadratics in year three as well for all of them. So year three comes back around to quadratics because they really deemed it as one of the most important ones. So if you did well in this unit, you're going to have a really good head start for when you start year three. So some of the things I'm going to quickly explain to you just so that you can see it, because they want us to make sure that you see it in year two, even if we don't do it or practice it. So remember, on these, you don't have to take notes. You just need to watch and understand and try to wrap your head around it. And if it is on the test and you should take notes on it, I'll tell you. So first of all, one of the important things to know about any of them, like if you're solving for x or if you're trying to get the x-intercept for the key feature one, the number of x-intercepts, how many there are, always depends on the degree of the equation. So degree is just a different word for exponent. So what this means is whatever the biggest exponent is how many x-intercepts there are. So for example, if I had 5x minus 1, the exponent on the x is an invisible 1. If there's no exponent there, it's just like an invisible 1 up there because there's one of them. So there'd be one x-intercept. And if you graph a linear like this, 5x minus 1, see how it crosses the x-axis only one time? Because it's a straight line, so it only crosses it once. However, if the exponent's a 2, then there's 2 x-intercepts, because it's going to cross it twice. Meaning if it's a 3, there's 3 x-intercepts. And if it's a 4, then there's 4 x-intercepts. And if it's a 5, there's 5 x-intercepts. And it's whatever the biggest one is. So if it was like this, and then it had plus 7x, right now, there's still 5 x-intercepts because the biggest exponent is a 5. But if I did this, Now there's going to be 8 x-intercepts because the biggest exponent is an 8. So the degree of this equation is 8 because the word degree just means the biggest exponent of it. So this one's called a polynomial that has a degree of 8. The word polynomial means more than one term. So this is a polynomial because there's 1, 2, 3, 4 terms. Remember, terms are separated by plus or minus signs. So like this is different than this because of the minus sign in between them, which is different than the 7x because of the plus sign between them. Up here, we talked about how we need to solve for x with quadratics. Cubic just means the exponents of 3. So, and that's why it says and other high degree polynomials, because cubic means that the biggest degree is a 3, but it could be 4, 5, or 6. And to solve for x with those, you do this process called synthetic division, and you'll learn that in year 3. It looks like this. It looks really confusing right now, and I promise when you learn the process, it's not too bad. But it allows you to factor out, and you're going to factor out factors. So let's say this is my equation. My biggest exponent right now is a 3, so it's a cubic. It's called a cubic when the exponents are 3. But also, it means it has 3 x-intercepts. So if I have to solve for x with it to find the x-intercept, I would make it equal 0. And to solve this, when there's tons of x's, I cannot use backwards order of operations. Can't use the quadratic formula because it's not a quadratic. And so the other option I had from the quadratics unit was to do factoring. Well, that's actually how you do it with any of them that are bigger than quadratics. You always have to start with factoring until you get to a quadratic. Because then once you have other stuff with the quadratic, you can do whatever you want to the quadratic to finish factoring it up. So here's what I mean by that. If I did synthetic division and to figure out what my factor was going to be, I would find out doing that math that you're going to learn in year 3 that I could divide 3x minus 1 out of this polynomial and end up with this polynomial. And this one happens to be a quadratic, x squared minus 3x minus 10. And if I were to prove that to you, 3x times x squared is 3x to the power of 3. 3x times negative 3x will become negative 9x squared. But then the negative 1 with this one would give me another 1, which would be a total of negative 10x squareds. Then the 3x times the negative 10 would be negative 30 x's. But then this negative 1 will times to this negative 3 to get plus 3 x's, which will combine to the negative 27. Then finally, the negative 1 times the negative 10 becomes a positive 10. So if multiplying it out, I end up with this answer, then it's true that once you do the synthetic division, you can divide it out and figure out what times what gives me that. So now that I have a quadratic right here, I could use the quadratic formula or factoring, or put it in vertex form with completing the square, then do backwards order of operations, whichever method I want to figure out what this can split into. I think factoring is easiest. To factor it, I need things that multiply to a times c, then add or subtract to b. So a times c right now is 1, c is negative 10, and negative 1 times negative 10 is negative 10. So to multiply to negative 10, I could do 1 times 10, with the 1 being negative. Is it the negative 10? So one of them has to be negative. Or I could do 1 times 10, where the 10 is negative. I could do negative 2 with 5. Or I could do positive 2 with negative 5. And those are my only two pairs. So then somehow I have to get to negative 3 when I add them or subtract them. So let's just put the plus signs because I put the negatives on the numbers. So in the calculator, if I did -1 plus 10, I'd get 9. And 1 plus -10 is -9. So it's not those two. If I do -2 plus 5, I get out +3. If I do -2 minus 5, or plus -5, I get out -3, which is the one I want. So it's going to be 2 and -5. Because this was the original, it's not like this part's gone. I just took it out and set it aside, and I didn't think about it. In this part, after factoring, I got x with +2 and x with -5, because the 2 I needed was 2 and -5. So this right here is the same thing as this. If I were to remultiply it all out, I would get this one up here. However, now that it's all in factors, I can set them all equal to 0 and solve them for their x-intercepts. So on this one, I would add the 1 over to get 3x equals 1. But then I would have to divide that 3 over, and then it would go away from this side, so x would be 1/3 for this one here. 1/3 is the same thing as 0.33. Here I would minus the 2 over to get x equals -2. So for this one, I realized I wrote plus 5 right here, even though it's -5 in the equation. So I need to put the minus. And then to solve it for x, I would have to add that 5 over to get +5. So if I were to take this and graph it, look, here's the graph. It's kind of all weird and curvy. It's like it goes up and then back down and then goes back up. And that's the shape cubics make. So they use cubics for roller coasters a lot. Like, all right. But if I look at the x-intercepts where it's crossing x, there's 3 of them. One right here at -2, which we solve for on this factor. The one at 0.333, which came from our first factor here. And then the last one over here at 5, which we solved for right here. So that's how it's going to get harder. That's how you're going to have to do it next year with adding synthetic division to it and everything you learned how to do in this class all mixed together. So as we were talking about it, remember one of the other words for exponent I was using was degree. That is not the only one. We can also say power, like it has a power of 2 instead of an exponent of 2 or a degree of 2. We can also say, so when we talk about it, we say raised to the power of, to the blank of. So you can say, so if you're looking at x squared, which has a special name because it's one of the special ones, so it's called x squared, but it's also called x raised to the, and then I could say exponent, degree, or power of 2. So I can use all 3 of those words to say x raised to the degree of 2, x raised to the power of 2, x raised to the exponent of 2. It all means x squared. I don't even have to say raised to the blank of. I can say has a blank of. So I could say x has a exponent of 2, x has a degree of 2, x has a power of 2. So that's just all many, many ways to say the exact same thing. If it's a 3, if it's a 3 in the exponent, the special word for that is cubed. It's x cubed. But then you would either say x has an exponent of 3 or a degree of 3 or power of or raised to the. There's a ton of ways to talk about x-intercepts. On the test that you're going to take, they're going to only use the word x-intercept, so that's great. On official exams like SAT and other ones, they might use other words. Words like solution. So whenever they give you an equation and they say, what's the solution? They want you to make it equal 0 and find the x-intercept. It's what they're asking for when they say, what's the solution? Also, they might say, what are the roots? Roots is just a word for x-intercept. Yeah. The last one they use is zeros. And the reason why is because the y is 0. So when you have nothing, it's when you're at 0 amount. So sometimes they call it your zeros. But so you might see any of these words, but they all mean solve for the x-intercept, and you can do the same process as you were doing before. If the number of zeros or roots or solutions or x-intercepts depends on the degree. That's why I kept saying there are always 2 x-intercepts for quadratics, because it depended on the degree. So if it was in factored form like this, the degree is secretly 2, because when you multiply it out, the x times the x will become x squared. And that's where the quadratic part comes in. Then x times 1 will be 1x. Negative 5 times x is minus 5x. And then negative 5 times the 1 is minus 5. When I combine these two, I get negative 4x. So it is a quadratic where the biggest exponent is 2, which is why when we factor it, we end up with 2 parentheses, and each parentheses will give us their own answer. So when I make x minus 5 equals 0, I add that 5 over to get x equaling 5. The x-intercept's 5, 0. And when I do it for the x plus 1, I would get x equaling negative 1. So the x-intercept's negative 1, 0. When I graph them, I very much see my 2 x-intercepts because it's crossing, the purple graph is crossing the x-intercept twice. But then what happens if both parentheses are the same? When I multiply it out, I get x squared plus 2x plus 1. A very normal looking quadratic equation. But when it's factored, I get 2 parentheses that are the same. So when I make the first one equal 0 and solve, I'll get negative 1. So the x-intercept is negative 1, 0. And when I do the second one and solve, I also get negative 1. Which means when I graph it, it's the same point. And so when you look at the graph, it's not crossing the x-axis twice. If you zoom in, it's only hitting this line once at negative 1, 1. So for all of them, for quadratics or any other higher degree, whether it's the exponents of 2, a 3, a 4, a 5, or even though the degree tells you the number of x-intercepts you should have, sometimes multiple are the exact same intercept. And when that happens, when you graph it, it looks like there's only one. When graphed, it looks like there is only one x-intercept. On some of the worksheets, this happens sometimes. And because it's just a thing, it sometimes happens where both x-intercepts are the exact same one. And so when you graph it, you only see one. This one's a quadratic in standard form. And if we tried to factor it, we'd need 2 numbers that multiplied to a times c. So 3 times 5 is 15. It's positive 15. So if I list everything that multiplies to positive 15, I have 1 times 15 and negative 1 times negative 15. 2 doesn't have a pair, but I can do 3 times 5 and negative 3 times negative 5. And then that's it. So then I need something that adds or subtracts to that b, which is currently what? It's currently a 4. So if I tried to add these all together, that's 16, that's negative 16. So not those two. 3 plus 5 is 8, and -3 plus -5 is -8. So not those two. So it can't be factored. So I wouldn't be able to solve for my x-intercepts by factoring. I'd have to solve it by the quadratic formula then. It's -b, and what's b? 4. And then we have the plus minus square root of that b being squared minus 4 times a, which is 3, and then times c, and what's c? 5. All over 2 times a, which is 3. And then if I were to do this math, -4, and if I put everything in under here in a calculator, 4 squared minus 4 times 3 times 5. 4 squared minus 4 times 3 times 5. I end up with -44. And what happens when you take the square root of a negative number? You end up with imaginary numbers, meaning your x-intercepts are going to be imaginary. If you remember when we talked about graphing imaginary x-intercept, it means that they're imaginary. So you don't actually see them on the graph. If I were to put this in the graph calculator, look, it's not crossing my x-axis at all. It's all the way up there. It has no x-intercepts. And it's because they're imaginary x-intercepts. So that could be true even with higher degree polynomials. You can have some of them that have no x-intercepts, or only one or two, because either some of them are doubled up and they're the same ones but more than once, or they end up being imaginary. So your x-intercepts can be imaginary, meaning that some of them might not show up on the graph. Meaning in real life, there's no x-intercept. Like if this equation was about how much money they have, that means in real life, they never had no money, which is very possible to have happen. Math exists in the imaginary world. It's a very complicated world to understand in situations what it means to have an imaginary x-intercept. It's very, very high level college. You're getting your master's in mathematics stuff. This is you just being introduced to it right now, which is why, even though it's true that this has two x-intercepts, they're imaginary ones that you cannot see on the graph. All right. So another way this gets complicated is one of the competencies is system of equations. And so in year one, you did it with two linear equations where you graph two lines and you figure out where they intersect or they cross. Like if I were to graph both of these, they cross right here when x is 2.286 and y is 5.857. And there are many ways to solve this. You could make them equal each other like this, where you put them side by side with the equal sign, and you solve for x. So you would add this half over to these, add these ones over to these, divide away, figure out what x equals. Then you would have to plug x into one of them to find the y. You would find out that x was 2.286. You take either one of them and put 2.286 in the calculator. You get out 5.858, which is exactly here 2.286 and 5.857. So they rounded differently here and here, but still, it's basically the same thing. If I put it in this one, 2.286, I also get out 5.85, and they're slightly off in decimals here because of the rounding. But yes, that's how you do it for linears. Now here, they could ask you to do it for two quadratics. It is super simple if you do it the same way. If you make them equal each other, like if you take one equation, you're trying to figure out where they equal each other, where they have the same point. So if I make it equal the other one, and then I just have to move the right things over, like at the minus this x squared over to this side, from this side over here. If I want to move it to the other side. Then I also have to minus the 3x's over to the other side as well to get rid of this side, and I would do it from the 4x's here. Because remember, you have to keep like terms together, so the x squareds have to subtract from x squareds, and the x's go with the x's. So then if you do your math, 5x squareds minus another x squareds is having 4x squareds. And then minus 4 minus 3 is negative 7x's. And then you have your plus 1 at the end. Then on this side, everything's moved over, so now it equals 0. So now it's looks like this, and you can solve it from either the quadratic formula, factoring, whichever way you want to do it. And you would find out where the two lines ended up crossing once you solved it. If I showed you these two on a graph, there's that one, and the next one was x squared plus 3x. So you see how the blue and the red cross each other twice, once right here and once right here. I'll zoom in a little bit. So they have this cross between the blue and the red, and that cross between the blue and the red. So by doing the math, once you solve for the x, what you'd be solving for, instead of x-intercepts, you would be solving for where these two lines end up crossing. So you'd get this x and that x as an answer, as your two answers, and then you'd plug them into one of the equations to figure out the y that goes with it. So this is another way they can make it harder by putting systems of equations with quadratics in there. They could also mix a quadratic with a linear. It's the same thing. You would just make them equal each other and subtract them over, and then use the quadratic formula on whatever new quadratic you get. The last competency they can do to make it harder is to do transformations of shapes and equations. And this one ends up being on the test this year. So they first introduced this as a unit in year 1. So hopefully you've seen these before. If not, I'm going to quickly review them so you can get this question right on the test. So transformation up here, this word just means to change. So when you're transforming something, you're changing it. You can change shapes around, or you can change equations around, because equations also make a shape, just like a quadratic makes the parabola shape. So let's just talk about them quickly. A translation is to move it. So you can go up or down, you could go left or right. That's just moving it around, up, down, left, or right. But the big word for that is translation. A reflection is when you flip it. Flip it over. With quadratics, like if you take x squared, to reflect it over, you throw a negative in front and see it flipped it down. And so it's called reflecting. It reflected down. And then rotations are when you spin it. So it's the square root of x that spins it completely sideways. I had to add in the negative square root of x because when I do the square root of x only, it only does the top of it because the calculator doesn't recognize the negative side. But when you put it in there, you see how it like took the parabola and it turned it sideways. So that's how you'd get rotations out of this equation. Rotations don't show up on the test. But basically what ends up happening is they give you one, and it might not be both equations, like one might be a graph and the other one might be an equation or something like that. But they're asking you, they give you one, and they say how from this one to this one, if this was the original one and this was the new one, how is it getting transformed? Like, how are you going from here to here? The easiest thing to do is whatever they give you, graph them both. So they're asking us, how did this graph go from here to here? And it's important to pay attention to which one they tell you comes first. So it says from f of x to g of x, meaning this is first and this is second. How is this one getting transformed into the other one? And you're going to use these things. Did it get flipped over? Was there a reflection? So tell me, is there a reflection of the graph? Does it get flipped over from here to here? Yes, it does. So that's one way, one of the things that you would say. So to explain how it got transformed, f of x got reflected, and that's not the only thing that happened. If it got reflected, it would look like that and flip over. It's not the only thing that happened. How else did the vertex move from here to here? If this one's at the x is 5, this one's all the way back at -1, is it going to go left or right? It's going to go left, and how many to the left? So here's 1, 2, 3, 4, 5, 6, until it gets to that -1. So it went left 6. It's moving left 6, but the big word for moving is translation. So, and translated left 6. Again, it didn't only go left 6, or else it'd be down here. It also went up or down. It went up, and then how many? This one's at 2, and this one's at 8. It's going up. 1, 2, 3, 4, 5, 6 to get to this 8. So f of x got reflected and translated left 6 and translated up. So when you get to the review activity where you're making your page of notes, remember it's very similar to the test. It's basically the test, but the numbers get changed so that I can help you figure out these types of problems before you take the actual test. So to end this video, I'm going to quickly run through the wording so you know what they're asking for. The first two just says write an equation. They say it differently. Explain how you created your equation, show your work. It means the same thing. Just do the math, and as long as you do all the math to get the equation the way you were taught in the lesson for getting the equation, then you'll be good in both of these. This one is a word problem. And so he's standing on the ground at 0 height, and he's shooting his slingshot into the air, and it goes up and it goes back down and hits the ground 7 seconds later. And it's telling you the rock reaches a maximum height at the lowest part of the bridge. So he's standing under a bridge because a ravine, it says he's at the bottom of a ravine. A ravine is at the bottom of a bridge, and he's shooting it up. So he's saying 100 feet above him is where the bridge is, and the rock actually hits the bottom at 100 feet tall and then comes back down. And so that's the situation here. Here they want you to create a graph of this scenario. So it might be easiest to start with creating the table and then maybe get the equation and then finally make the graph, even though that's the backwards order, because here it's not till part C they ask for the table, even though it might be the easiest one to start with. Then to write a function means equation. So then you write the equation and then you can create the graph. It's saying that the graph should include at least your x-intercept, y-intercept, and vertex. So should your table. It says later on it should at least have those. But it's saying a complete graph consists of labels, meaning you'd label like height of rock for the y-axis, and the x-axis you'd label like time that's gone by. And then scales mean like how much your tick marks are worth. Ordered pairs for each identified point, meaning like, let's say you find an x-intercept is like 7, 0. When you graph it, they want you to write this next to the point for a complete graph. Then they want the equation here, the table here. And then this part's weird. It says identify how you see the x-intercept, y-intercept, and vertex in the table, graph, and situation. So in the table, you can highlight them and write or circle them and write x-intercept next to it, y-intercept, vertex. Same thing on the graph. Like if you put the points down next to it, you can write x-intercept or y-intercept or vertex. But for the equation, it's harder, and it says hint, you might need to rewrite the equation in equivalent forms. Because remember, if it's in standard form, then in standard form, you can quickly see the y-intercept because it's the one at the end. Like in this case, it'd be -5. And so you'd have to have it in standard form for the y-intercept. But to show them the x-intercepts in the equation, you'd want to put it into factored form, where it's the 2 parentheses. Because that's how you quickly see them, the x-intercepts, because it's the opposite of whatever you see here. So you'd have to put it in factored form. And then for the vertex, you'd have to put it in vertex form and show them like highlights. Like I'd highlight the -2 and say +2 for x because it's the opposite. And then like an arrow for the, so I'd go to show from vertex form how to quickly get the vertex. It's gonna be 2, 6. And then I just go like this. And then next to this one, I'd write the opposite because that's how you do it for the x's. You get the opposite versus this one's the same. So this question is a lot of work because they want you to take the situation, they want you to graph it, and then they want you to identify the x-intercept, y-intercept, and vertex in all 3 forms. And it's easy in the table and graph. But in whatever equation you have to come up with, you have to rewrite that equation in all 3 forms. So if you start with vertex form, you have to put it into standard form and then in the factored form to point out where you can see them all quickly in the equation. It's a lot of work. The next one's even more work. And this one can get confusing, so I'm just going to quickly explain. They give you 3 different things. This one's f of x, this one's g of x, and this one's h of x. This is a table. These 2 are equations. First, they want you to identify the key features for all of the functions. So for all 4 of these, they want you to figure out all the key features. Note that they're asking if the vertex is a maximum or minimum. It's really easy to figure that out. So for this one, for example, it's at -9 and around it's -8. If you were to graph that, -8 is higher than -9 on the graph. And so that means this is the lowest point. So it's the minimum. So basically you can graph it and see, is it at the top of the graph or at the bottom? And you'll see if it's the maximum or the minimum amount. Stretch/shrink remembers the A in front. You do it for all 3. And then in part B, they want you to compare and contrast G and H. So they specifically in this one only want you to do these 2, the G and the H. And they want you to compare the 2 functions. And they're just saying, for the rest of all these words are just saying compare everything. So compare the x-intercepts. So you'll compare the x-intercepts. Do they have any that are the same? If not, which ones have bigger x-intercepts? Which ones have smaller x-intercepts? Same thing for the y-intercept. Whose is bigger, whose is smaller, or are they the same? Same thing with the vertex. Whether or not the vertex is a minimum or a maximum, maybe for both, they're minimums, or maybe they're different. But just talk about it. And then finally, the stretch/shrink. Is it stretching it? Is it shrinking it? Are they the same? Are they different? So that's about G and H that they want you to compare. Then for part C, they want you to do the same thing, but for F and H. So for the last one and the first one. So you're not comparing all 3 to each other. They're telling you which 2 to compare in each part. Then part D compares F and G sort of, but someone else compared them and you're telling them whether or not you agree. So he's saying that the function g of x, so this one, the g of x one, this equation, can be obtained, so that just is a big word for can be got, like you can get it by translating, so by taking the f of x and going left 2 and up 7. Do you agree or disagree? So that's that transformation stuff that I told you they brought into the test. So the easiest thing to do, like I told you, is to graph both of them. Look at them on a graph and tell me to go from the F to the G. Are you going to go left 2 and up 7? If the answer is yes, then it says if you agree with them, then demonstrate, so that means show his correctness through a common representation of the two functions. So you can choose to do it with an equation or with a table, but you have to really know that unit from year 1 to remember how to show it, or in a table or in an equation. However, in a graph, it's really easy because you can see the picture moving. Like you can see the vertex moving, like I showed you, like it's visual. So if you graph them both, then you're doing that. You are doing this part of the instructions if you graph them both to show that it is going left 2 and up 7. If you disagree, all you have to do is tell him how it's right. So tell him what the right translations are. And then also provide him with the series of right transformations. So tell him what to do. And then demonstrate them through the common representation, meaning the easiest one is to graph them both to show it. So it's either you agree with him and make a graph to prove it, or you disagree, explain why you disagree, and then make a graph to prove it. Would be the easiest thing to do, unless you remember how to do it one of the other 2 ways and you like doing it a different way more. And that is the entire test. So go ahead and practice this page of notes and put your answers into that slideshow Pear Deck thing, and then you'll be ready for the test.